Today, we are digging, quite literally, into a huge question in environmental science. How do we actually know how much carbon is locked away in our soil? Well, it turns out the answer is this fascinating story that involves some seriously clever chemistry.
And it all starts right here, in a simple handful of Earth. Now, this isn't just dirt, it's a super complex, living ecosystem. It supports our agriculture, it filters our water, and crucially, it plays a massive role in the global carbon cycle.
So, that's the big question, isn't it? How do we read the secrets that it holds? I mean, how can we put a number on its health and its potential to help our planet? Well, that's exactly what we're going to figure out. To really get why scientists go to all this trouble, we first have to understand just how important soil organic matter, that rich, dark stuff full of carbon, really is. Okay, so healthy soil organic matter is just incredible stuff. It makes soil way more fertile because it holds on to nutrients, and it improves the actual physical structure, helping it hold both water and air. It's basically the fuel for the little microbial engines that drive the whole ecosystem. And by doing all that, it means we don't have to rely so much on chemical fertilizers, which is a huge win for the environment. So how in the world do scientists measure this vital component? Well, it kind of plays out like a chemical detective story, and the main piece of evidence comes from a classic, time-tested procedure. The technique is called the Walkley-Black method, and the core idea is actually pretty simple. You basically force the carbon that's in a soil sample to react, or what scientists call oxidize, and then you measure the results. It's a foundational technique you'll find in soil labs all over the world.
And this right here, this is the aha moment of the whole process. The key chemical they use, potassium dichromate, is this bright, vivid orange. But when it reacts with carbon, it transforms into chromium ions, which are a deep green. This color change is the first, totally unmissable clue that we found our target.
So here's what's actually happening on a chemical level. Think of that orange liquid as a powerful attacker. When you mix it with acid, it goes after the carbon in the soil, ripping it apart and turning it into carbon dioxide gas. And in that process, the orange chemical itself gets transformed. And that's what gives us that really vivid green color. But here is where the real genius of this method comes in. Instead of trying to measure the green stuff that was created, scientists do something much smarter. They measure the orange stuff that wasn't used. This is the key. It's a concept called back titration. And here's an easy way to think about it. Imagine you have a full bucket of water, and you use some of it to put out a small fire. Now, to figure out how much water you used, you could try to measure the messy puddle on the ground. Or you could just measure how much water is left in the bucket and subtract that from what you started with. Way easier, right? That is exactly what back titration does. Okay, so let's walk through it. First, scientists add a very precise known amount of that orange oxidizer to the soil, and they always add more than they'll actually need. Then they add concentrated sulfuric acid. And this is cool, the mixing creates its own intense heat, about 120 degrees Celsius, which is what really drives the reaction. After 30 minutes, they do the back titration to measure exactly how much of that orange oxidizer is left over. The difference tells them precisely how much carbon was in the soil to begin with. Now, what's so interesting to me is that science never just stands still. Even with a classic method like this one, there are always new questions, always refinements being made. And the big debate here centered on that self-generating heat. Was 120 degrees really hot enough to oxidize all of the organic carbon in every single type of soil, or was some of it getting left behind? And it turns out the answer was no, not quite. The original method, just using that natural heat, only recovers about 77% of the total carbon. To get closer to a full 100% recovery, scientists found that you actually need to add some external heat, bumping the temperature up to 150 degrees. So how do you fix this without changing the entire procedure everyone knows? Well, they use a simple but pretty brilliant correction factor. Knowing the method only finds about 77% of the carbon, they just multiply the final result by roughly 1.3, and that gives them a much more accurate estimate of the total organic carbon. It's just a simple, really elegant mathematical fix for a chemical problem. All right, so let's bring it all back together. Let's connect all this precise work happening in the lab back to the land itself. Performing this analysis requires some incredible precision. This is not your high school kitchen chemistry. We're talking about analytical balances that can measure to a 10,000th of a gram,
perfectly calibrated glassware, and all this specialized equipment like magnetic stirrers and burettes, all of which has to be done safely inside a fume hood. And this brings us right back to where we started. All of that precision, all of that really complex chemistry, it's all dedicated to one single goal: to accurately read the story being told by this simple handful of soil.
Of course, it is so important to remember that this chemical detective work involves some pretty hazardous materials. The type of chromium used here is toxic, and concentrated sulfuric acid is extremely corrosive. So safety protocols, wearing the right protective equipment, and responsible disposal are all absolutely non-negotiable in the lab.
So we've seen how this clever, nearly century-old chemical test lets us measure something that's absolutely vital to our planet's future. It really leaves you wondering, if this is what it takes to unlock just one of soil's secrets, what other incredible mysteries are just waiting for us, right beneath our feet?